Welcome to today's webinar. The topic today is modeling and design of steel structures in RFEM6 and RSTARP 9. My name is Andreas Hörold. I will be the moderator today. I'm responsible for marketing and public relations in the Dlubai software company. For instance, the Dlubai website, the German and English webinars, press releases, etc. My colleague Andreas Niemeyer will introduce himself.
Hello, I'm Andreas Niemeyer. I'm responsible together with Mr. Dlubai for the development, and in detail I take care about the R-wind analysis and form finding analysis.
Okay, thank you, Andreas. Our two colleagues, Frank Faulstich and Oliver Metzges, will support us by answering the questions. You can ask questions via the control panel on the right side of your screen. We can disable our webcams so that you can see the full screen. Okay. Yeah, here, as you can ask questions here in this field. If you don't get an answer during the webinar, because there are too many, you will get an email after the webinar. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, first point is modeling a steel structure in RFEM6. On the right side, you can see the full model, the completed model. The second point is the load input and combinatorics. Then Andreas will design the structure according to Eurocode 3 and prepare a documentation in the printout report. Then I hand over the screen to Andreas. Okay, it's your turn, Andreas.
Okay, thank you, Andreas, for introduction and also displaying a picture of the model what we want to model together the next hour. Let's say it's a bigger challenge what we want to do here with the complete modeling of a steel hull, the loading combinations, some organization parts and also the documentations, but I take it over and try to show it how you can handle it in our new RFEM6. So for this, at first we give a model name. Let's call it base ENU, and let's use a type of model 3D. We started with a blank sheet and define in the next register the add-ons, or let's say our tasks, what we have to do. So at first we want to design steel, or in the final we want to design the steel members according any standard. Therefore I activate the add-on steel design, and because I assume we have to make a analysis if we have to design the model according first or second order, I activate the add-on structure stability. These two add-ons, let's say, modifies the menus in back and offers us all options we need for these two tasks. And because we want to design something according any standard, we have to select the standard in the next tab, which standard we want to use. You see we have here three open options regarding combinations, regarding load wizards, and regarding the steel design, and I can select here the standards what are offered, let's say here Eurocode, American, Canadian, and so on. But even for European standards we have all national annexes. So for today I plan that we build this steel structure in the garden of our boss. Therefore I select the German annex, for the wind wizards also, and for the steel design also. And the program writes us down a list of standards which will be used for the model in background. And after this, or maybe to sum it up, because it's quite new, if we select here a steel design, this is now our new add-on. Let's say compared to the add-on module to RFM5, we purchased every standard separately in an add-on. Here it's different. You have all standard in one add-on. So if you select steel design, you get all standards what are written in this box directly without charge also. So it's a, let's say, a pretty big add-on, and the same for concrete also. So if you select concrete, you get all concrete standards and also all elements, what means punching nodes, beams and slabs. So with this philosophy, what we overtake or what we created now in RFM6, you can select your tasks and order your add-ons what you need. So let's go to the next sheets. I select for our, let's say, model some member representatives. This is, let's say, a smart idea to organize your model and to input your design settings quite efficiently. How this is working, I will show you during the presentation. And in the last register, I want to define the site or the place where we want to create the steel hall. And as mentioned, I want to place this model in the garden of our boss. I write maybe here Global, because I don't know the address, but I can use the Google search for it and say find for us maybe the German department here and place the pointer on the map, let's say exactly on this address. I get here altitude, longitude, geo coordinates, and now I can zoom in and can place it exactly where it's built. So we can zoom into the map like in a regular Google Maps application also. So let's change to satellite. Now we can say we place it here and get now exactly the data of this place. If there is some hill or mountain, we get here exact altitude for detecting snow loads. After overtaking this setting, the program transforms now the geodata, let's say in syntax of our address into the menu, but also the geodata regarding snow load, wind load, and earthquake load, and give it to the results of the program. How this is working, I show you at the point when we place loads. So now we opened this model with the predefined standard and steel design, and you see it looks almost similar like in RFM5, but it isn't. If you take a closer look, you see we changed our navigator a little bit. We have now a clear collected shape that we have here basic objects in one arm, and we have to every basic object when it's possible also a type for it. So for example, we have a basic object node, and then you see you have also here type for nodes. The same is for members, for example, we have type for members. And this logic is now made for the tables, because we suffered in past that we get a lot of tabs or registers into the right side, and this option gives us the possibility to have only a clear amount of tabs in one row, and if additional information is needed, we can change the type. So if you go here to this two combo boxed organized table, you see we have the same logic like in the navigator here. You have structure, and then you get basic objects or type for members, if you go, or type for nodes. If you go to type for nodes, you have only these two tabs for type for members, maybe all what are available, but it fits into the monitor with this. And this helps to understand always the data what is here and to find all what is needed. So, and now let's start modeling with the first members. For the steel hall, we start with the modeling of the frame. Therefore, I change my grid plane into the CX plane and place the first member. I go to new member, define here a section, maybe an IPE 300, and place it here on the origin. And now I want to define a 4.5 meter long column. And how to do this, because the grid points are only offered for 1 meter distances. So I place my mouse pointer maybe in the direction that the program has the vector and write 4.5, and the program gives me a 4.5 long member. Then we take or we select this member and copy it on the right side, maybe here by 13 meters. So good. Now we have to place a roof on the two tops of the columns, and we know the ridge is in the middle. Therefore we need a node in the middle, and for 30 meters we can calculate it by hand, but maybe if you have a not so nice dimension, we developed here a function, create a node between two nodes, and you can now pick maybe the left one and the right one, and the program generates us here a node in between, and this is adaptive. This means, you see, it's connected still to the outer nodes, and if I move one, this node will be also moved. So we can, but of course this, or let's say, because this connection, we can also select it. So we can take it and can create a new node from it. I use a other manipulation, go here to the chamfer solution and say, please copy me this node with an inclination of 13 degrees, rotate it about the y-axis and move it into Z direction. And please rotate about this Eve here and create it. And now the program creates me in the center a ridge node with the inclination of 13 degrees. And now I can place my roof members on this construction, and the rest node I can delete. Now, when we create such a member, we generally want to, let's say, create a member which have here a bigger cross section than here in the middle, because the bending moment is here bigger, so we want to taper it. And in past we modeled this stuff by two members, but now our program offers here, let's say, a macro solution. We have here a section type with distribution type uniform, or let's say linear, but also now new, tapered on both sides, tapered at start. You see, there are offered different shapes of cross-section distributions. And for our task, we take here tapered at start of member, define here maybe the tapering is running until a quarter of the member length, and we say that the top side is straight. So we can also place here internally eccentricity. And now we have to place some cross sections. So we say in start we use maybe this one and go here to modify. Let's check this, which cross section this is. Oh, it's a parametric I section with a height of 220, a width of 110, so it's fit so far. Let's create from this cross section a second and increase the height to 600, for example. And now place this cross section here. In start of member we can use the 600 millimeters. In the middle, so in the end by point J, we use the smaller one. And this gives us the option now to place the macro member by 2 points, and the program creates automatically this tapering in one member. So if I move this node, the tapering is also moved, so it don't remain on its origin place, what is quite helpful, I would say. And now we can take this member, can mirror it on the other side, so I create a copy with the plane YC, and one point of the mirror plane is maybe this ridge point. So this is maybe our first frame, and we can start going into the third dimension. But before we copy it into the third dimension, we create, let's say, connection point for bracings. So connection points for bracings, let's say I have here, I want to divide these members into 3 parts. So I make 2 intermediate points, but I use a function create node on member. This helps me because if I move the ridge, these nodes remain on the member axis and they don't divide this member, what is helpful for further design definition. The same I do for the columns. So I select these columns and divide these members here by 1 node and create node on members and confirm this setting. So now this frame is so far ready for copy step. I select everything, but I remove this, let's say, edge point between tapering and straight member I remove. Then I open the copy command. I say let's copy 3 elements and the displacement vector is maybe -5 meter, and I activate in the options a function link steps. This means I create between the origin node and the copied nodes new elements, let's say linked members, coupling members. For this I say please link nodes with members, and because he don't know which member he should use or specification, we say please create here a template. And the template for me is he should create truss members in between with a cross section of, let's say, a circular hollow section, for example. So let's go to the library. Let's use here circular hollow sections and select here cross section maybe with 17 centimeters with a thickness of 8 millimeters with, let's say, the better steel material. So, and after confirmation, the program knows now for the copy step a template, and if we confirm this stuff, the program creates the copy of 3 frames plus linked members in between for all nodes what we selected. Now we have to secure that the, let's say, frames remain in its plane, so we have to add some bracings. For adding some braces, I use some truss members. Not truss members, let's say some tension members. So I use a member type tension. Go here to library, use here a solid section, and use here, for example, this round cross section with 20 millimeters and place it here between these cells. So maybe you just realized it, that just the color of this rectangular shapes changes, so on this colored block, and after I picked some members. If I do it again, maybe again I pick the information of this member, so tension, and define here a cell, you see the program changes the color of this block symbol above the member. What is this? This is a representation or a symbol of the representatives. So if we go here to representatives, you see the program selected or defined here 5 representatives. He sees that, for example, this dark blue color represents a column, and the program finds out that all these columns are similar. So he selects directly all. The same for these beams on the roof. He finds out that all these 8 members are similar. And because when I define a new member, these representatives algorithm runs again and finds new one. So if I copy now some representatives, or let's say members, which have the same properties, nothing happens. The same for the, let's say, roof bracing. But we see that the roof bracing have another color like the wall, because these members have a different length. So now let's mirror these bracings on the other side. And for this I select here the solid members in the table and use our mirror command and create the copy without link steps and go. So this was everything about the outer wall. Now we have to close the gable or front walls, and for this stuff I use maybe this cross node from the bracing. I select it and copy it down to the bottom. For this I use only one copy, define the vector from here to the bottom, and the x dimension I 0. Now we can also link the steps and can create a member in between. This is not a circular hollow section and no truss. I take a beam section for it. And the beam section should be here maybe an AGA. We define a new one, and in the past or in the last steps I always open the library, but you can also write here a name, AGA. For example 200, and the program offers you all from the cross-section list. So I can select it and we get directly the cross-section what is connected to this name. Okay, and because it's in the front walls I have to rotate it maybe with -90 degree. And after I confirm it and confirm also this dialog, we get the column here in the front. You see a new color because it's a new type of representative. And now we can, the only thing what I always changing is that it's running upwards, so I reverse orientation and add a hinge on the end. So let's place a hinge in properties and say we have here a hinge in the connection to the roof, maybe about both axes. A weak and strong one. So, and now it's ready. We have the column, and the next step is that we have to bring in some connection points to the column. So I use, for example, here these nodes from the outer column and copy it by drag and drop on this column. And now I merge it with the column. So I double click this node and change it to type of member. Say it's a part of the member 70, and I define the place it's here on this coordinate of member. After confirmation it changes its color and will be now a member on a node on member. So the same for the upper one, member 70, and the place is this one. Now it's the point where I change the model from transparent or solid one to wireframe, because I see more. And to see the cross-section orientation, I open in basic objects below members the member outlines, so you see exactly which cross-section is assigned. And now we can take, for example, these outer 3 members, copy it on the other side, and move the node to the just prepared node on the AGA column. So Now we can close the wall like this. We copy again this column here on the other side. Take with a selection step the 3 horizontal members and now close the top with this beam. You see, this was quite easy to fill this wall with the right members, and now I only draw a simple line on the bottom but have no statical or structural effect. It's only for closing. Why? You will see afterwards. The only thing what I'm doing is now I select here the complete wall and drag and drop it on the back. And you see this was almost everything what is needed for the wall. We can activate again this transparent modeling. You see, oh, this is not really nice. Therefore I select these beams and say members, edit, section type not. Please use only a uniform type with the smaller cross section I220. So now it looks a little bit better. So almost finished. The only thing is we need some boundary conditions. I want to simulate some base plate. So here to overtake loads, I change these members to a rigid one, to a coupling hinge. This member will overtake the force from wind and transport it directly to supports. And support was the keyword we place here also on the bottom legs of the members, a nodal support, a hinged nodal support, only by drawing here a window about it. And you see the program draws a picture of the symbols, and if you have the feeling they are too small, you get now here such a let's say spin button, a horizontal where you can only specify the right size of these supports. The same is offered for loads. And now we are at a point where we can go ahead with let's say loading. The keyword loading brings me to the steps that I display the table and jump into the, let's say, chapter load case and combinations. And you see the program automatically defined here a load case serve weight, but it considers only the weight of the members itself, no additional weight. Maybe if you have some trapezoid sheet or some covering whatever which have a weight and you want to consider it. And if you want to consider such a surface weight on members, we offer more solutions. One solution is, for example, the wizard solution, member loads from area loads. And this wizard is here for defining a load as maybe surface load, maybe here 10 kilogram per square meter, in direction into C direction, into the load case surf weight, and brings it to the members via what creates then from the surface loads member loads. And for this stuff, for this definition of surfaces, we offer now two solutions. In past, we have maybe one solution for defining a surface in space and one solution for defining cells in space. Now you have both in one. Let's take a look how this is working. So I say, please find me cells, and you see the program find many cells on the structure. Maybe this is too much, we will remove it, but it find no cell because the cell is open to the bottom. And for all cases what he don't find, we can define now and say, okay, for this part we define the loading plane manually by defining the outer corners. So the same for the back wall. Oh, not this one, then this one. And rotate, and now close the gate also on this wall. And now we have covered the full outer, or the, let's say, the full hull of the all, and with confirmation of this wizard you will get all loads on this structure. It looks nice at the first view, but if you say please show me the member loads in background, you can use display separately, and you see he will distribute it on all members what are available. Of course it's not expected here, but you can modify it. So you can say here, for example, please remove the influence of all members which are parallel to this vertical member, or parallel to this member, or parallel to this member. So if you confirm this, you will see the program will not load these vertical members and only this horizontal member. So this is possible, and you can apply quite efficiently loads on member structures with this function. But I want to show you today a more smart solution, or what, let's say I like it more personal. And therefore I delete this. Okay. And I change now to surfaces. I take here a look on select, I use the function select boundary and use a surface with the stiffness type load transfer. This is a surface, you see the similar picture. It's a surface which have no effect for structural analysis, but it overtakes load and transport it back to the members or all other objects what are in this loading plane. So let's define it for this structure. I pick the boundary elements. This is of course a work step what have to be done, but it have to be done only one time and could be used for all type of loads. So close this roof side, the other roof. Oh, this was a wrong member. Nope, nope. Now this vertical wall. And now the gables. And again the other gable. Of course you can also try to copy it. What's your favorite? Now you see we covered it with a surface, and now the question appears how we want to distribute loads. For this load distribution I display now the coordinate system of surface. Yeah, you see the y-axis is running vertical here in roof direction, the same here and the same here. Therefore I select these surfaces, go into the options and say please transfer the load in direction of y-axis, and okay. And the same for the, let's say, for the gables, but here it's a little bit different because I don't want to connect to the roof beam. Therefore I say please distribute loads in both directions, but without considering the outer members like the columns and the roof beams. The same I define for the back wall. I say here both directions without influence of these members. And after confirming this construct is ready for loading. For example, if we want to consider self-weight, I select everything and define, for example, surface edit. We have a load of surface load of maybe 10 kilogram per square meter. And you see nothing right now because surface weights are hidden. But if you say please show me the separate loads, you will see the surface will distribute the weight of its own surface weight to the members like this member loads and distribute it with this law what we defined. And we can use this definition now for all type of loads. So let's bring up, for example, a snow load. We can write it down here or we can use a wizard. So let's use a wizard. Go here to snow load wizard. and define, for example, for a dual pitched roof, the outer coordinates. So maybe here the left eave, then the ridge node, the right eave, and again the ridge node, and confirm this. Then the program realizes we have a dual pitched roof with roof 1 and 2 with this inclination, and defines the parameters. And here maybe you see the interaction of the definition on the Google Maps application. We overtook the geo information from, let's say, the place we defined on the map with geo coordinates, with altitude, but we get also on this place the right load zone, and the program detects automatically that we have maybe here our typical Bavarian snow load of almost 250 kilo per square meters. And this is everything. So we have to define nothing here. Of course you can modify it, but you can overtake it from the global setting. And now the program, the next topic is that it will create 3 load cases, maybe full load, and change it to the different sites. For my presentation, I think it's enough to have only this basic case, and here I create 1 load case for it. And with confirmation, we get, let's say, the snow load according standard placed on the model, and because he finds this load transfer surfaces, it will distribute the load directly to the members, which should be selected according to distribution surfaces. Then we can go to the wind loads. Of course you can use now the generator, but we haven't. So I can use also here maybe a manual wind, so wind in X, and let's define it here, define a load type, and place the loads on the structure. So for this I use now surface load, and let's define load direction. The size, for example here 0.64 on the pressure side, so define here the pressure side like this here, okay, and apply as next. Then we can take the suction with 0.4 for example, it's this side, and confirm it. Apply next. Then the outer suctions in Y direction with the size of 0.8, and here to this surface, and okay, and apply as next. And now the back wall with minus, and define it here in this direction. Of course we know, or I know, that we have a load skin on it, but for presentation I would say it's enough. Now we have maybe also a suction on the roof, so I use here minus 0.35 and place it on these 2 roof surfaces. And without big effort, the program creates from this easy setting all member loads on the structure what are needed from it. So this wind load case is almost similar to the wind in Y direction. Therefore I copy it. I go to load cases, copy this load case, copy load case into wind in Y direction. I change the name and confirm it, and now we only have to change, let's say, the load forces or magnitudes. Therefore I go to the chapter loads, wind in Y direction, and now let's start here with the pressure side. So it's maybe this load here in the back. I start with this row. We have here 0.64, 0.4, in X it's 0.8, and here we have minus 0.8. So this is, let's say, for covering a relative bad situation for wind loads for demonstration. And now we can work with these load cases, what brings us to the topic of combinations. Of course, the program, oh, we forgot one load case. Go back to load cases. We need a pre-stress. Pre-stress. We use here category pre-stress and go here to tension members and say in the member loads, please use here in the tension logs axial displacement with -1 millimeter, for example. And this should be used for all tension members. Yeah. Now we have all load cases, and this brings us to the case that we need combinations. Of course, the program knows this and already prepared load combinations, and you see we get a list of load combinations. The only question is, should we calculate according second order p-delta analysis or not? And this we can evaluate by doing some structure stability analysis. For this, I open my combinations, go to the, let's say, design situations, what cover the state of everything, and say, of course, the characteristic ones should be calculated always linear. For the red one, for the ultimate limit state, we are not sure. Therefore, I define, let's do for this a stability analysis and do a linear calculation. You see, I checked only this option, and this means now that the program calculates for all load combinations in background a stability analysis eigenvalues for this load situation. And if we start now the calculation of this design situation, which covers this, we get results for the, let's say, structural analysis. You see the internal forces and eigenvalues for this same set. So we have to do the double or the calculation twice, one for structural and one for the eigenvalues, but you get both in one by only checking one option. So you see the internal forces and deflections already calculated, and now we go to the eigenvalues, and now it's done. Good. Yeah, results are here. You see directly some deflections, and even you can activate some internal forces, but this was not the case. We was interested in eigenvalues. And as you get here in the table the static analysis, you get now also the stability analysis. And you see, maybe let's deactivate here the forces and activate deformation section colored. This is the first eigenvalue of load combination 1. You can also change here to the different eigenvalues what are calculated. And by switching here the load combination, you get also the eigenvalues of the others, what we activated for. So this was everything in one step, but now the question appears, what is the most critical one? And for this we created an option in the static analysis below the, let's say, design situation, and you see the sum up table gives us information what is the minimum critical load factor of everything. In this case 5.15 in CO2. Let's take a look on it. Stability analysis, CO2, and you see here is the critical eigenvalue. It's a global shape into X direction, and because we have a magnification factor bigger than 1.1, we have to consider second order calculation with imperfections. And this is the keyword, so we have to define some imperfections for this stuff, and therefore I go here to the base navigator and open here the arm imperfections between the topology data and the load data. And imperfections are now ruled in RFM6 not with load cases and with imperfection cases. Something similar to load cases. I can create the imperfection case with different types, but I use now local imperfection with the name imp in X and assign it to the wind in X direction. And now let's fill this imperfection case by some global imperfections. For this I use now these solid blocks, so these representatives. I select, for example, the representatives for this column type and additionally this representative for the gable columns. And if I say, please show me the visibility of all these, you see I can directly create with these visibilities, for example. Now go to the imperfections into X. For this I activate the member axis system and create here imperfection maybe according Eurocode into Z direction with the base value, and the column height is, for example, here 4.5 meters, and I have in the mid columns 2 columns in one row, and now we can place the imperfections on these members. Okay, apply and next. Then we can go to the next one. We have here 4 columns, so apply it. We can activate it also to these columns. Oh no, to this not, because it's rotated, so only to the outer ones. And okay, apply it next. And now to the gable ones, because we have to use here minus y direction. So minus y direction, we have here different height, maybe here 5.5, and place these imperfections on these mid columns. So this was everything for imperfection in X, and now we can place an imperfection into y direction. So here again, like for the wind load case, I open this imperfection cases, copy this case into y direction and change the values. So here I open the sheet. No, it's not needed, so I can select all imperfections here in this graphics. So I select it here and say right click, edit imperfections. Now in this case in y direction, the height is fine, but we have 4 columns and fine, good. And now let's change the imperfections for the mid column. Here select, edit members into, we have here Z direction, Z 200, height is correct, but only the amount. So, and now even the imperfections are defined. And because we have to calculate according second order, we can go now to the combination, edit, and say in the wizard for the combinations, please create us now or combinations according second order. Stability analysis is not needed now anymore for the imperfection cases what we assigned. Okay. The only thing what I forgot was that we have to assign this y imperfection into wind in y direction. So now we get even here the imperfections or the load cases according these definitions. We see assigned imperfections, and you see that the program created us some combinations doubled, because we have here for pure self-weight imperfection in X and in Y direction, because the direction is unclear. But for situations where we have a clear wind direction, we have imperfection in X, and for another one where wind is in Y direction, imperfection in Y direction. So this was everything regarding the combinations, and now we can go to the design of everything. The design is now generally done. So if you model something, RFM6 thinks he prepares everything and he prepare all data what is possible, but what could be not done is the stability setting. So if we take a look on our beams, we will see that we have maybe here roof beams which will be braced at these points. And for this we can open, for example, this representative and can say we have a bracing for the stability check. For this I go to design types, open the boundary conditions and say yes, we have nodal supports. Please consider it for this type of member and fix maybe here the lateral deflection direction for the second and third node, and define for the first one maybe an inclination of -13 and for the last one also -13, and place it on all types of the representative. And if we confirm this, you will see that the program places here on these members buckling conditions. So we can activate it here by this option, and you see the supports are placed at these nodes. The same for the outer ones. So if we select the outer representative, where we can say we have now here effective flanks, we want to check buckling in both directions, plus torsional and lateral torsional buckling, where we say please according this member, where we fix the first node only in horizontal direction and the second in both. And after confirmation, you see here this node is only checked in horizontal and this node with the column is checked in both. The same job we have now to do for both, but I forgot something. Maybe for this roof, we can also add some shear panel check. So we place here maybe a trapezoidal sheeting where we say it's placed on the upper flange, maybe for this sheet with a height of 160 millimeters. And we have a shear panel length of, for example, 50 meters with a beam spacing of 5 meters. And now we can place even this stiffness type for this roof element, and even for the, let's say, other roof element, we can use also the shear panel setting. So this is quite easy with these representatives because I can distribute the setting to all connected members which have these similar properties. Now let's go to the columns. So for example, this representative needs a buckling check for all directions, but all the columns will be braced in the middle for the weak axis, and for the strong axis we have a increase of buckling length with a factor 3.5, for example. Yeah, quite easy to distribute. So even now we have defined members, roof beams, gable beams. Now these roof gable columns are missing, so we can also add here effective length setting, maybe here to consider, let's say, at least these intermediate points. And you see this is maybe done also for these elements, and he always places these supports on the nodes what are available in the member. Now the only thing what is missing is maybe these bracing members, and here we can take the same setting like for the last one, and even for the last representative we can also take this setting. And if we check now all positions, you see coupling members we don't have to check, tension members also not interesting for bracing. Here this member is braced in this direction, this member here, Here we have also this shear panel. So every member have a buckling setting what is was needed, and now we can open or we can close this environment and can go to the design. To the design, we can go to the steel design, and you see you have here some input data where you see we go, let's start from the first tab. Here the program realizes our design situations for which it should do a design, for which members it should do a design, for which materials, sections, and which details should be used for design. Here, let's take a look. Is written the tolerances, if it should check the stability, if it should maybe use some special options, maybe double banding options for stability check. And you see these settings could be assigned to every member, could have different settings. The option is on you, yeah. And yeah, with giving all this information, we can start the calculation and go ahead here. Okay. Then you see the program prepares all load situations for doing the design. He needs the load combinations for ultimate limit state and for serviceability, and now he's jumping to the design add-on for designing the members. Everything was defined in background to do this only with our stability settings. Now you see generally everything is fine. The only thing, some members are not fine, where you have to work, not where you have to work, and where you have to check what is not working here. So let's go into detail, select one beam and take a look what is not fine here. You see some gaps are okay from utilization, but not everything. The design add-on gives you here an overview table of all options. He says maybe you have overutilization for stability and for section proof. You can also give this information or take this, check this information in detail for maybe ratios on members. And you see if you select, for example, this roof beam here, he jumps into the right chapter, and here it's obvious, okay, we have maybe some cross-section issue. Yeah? If we go to this check here and open the details, you will get a overview about which values leads to the utilization, which internal forces are used, and you get also on the right side display of the formulas, how the program come to this value with a clear description. This is not only a steel feature, and this type of display is offered for all type of design checks, even for concrete and for aluminum and so on. You get always the full calculation of every value in this formulation style with a clear depiction of value. And if it's needed to know more about in let's say dimension of cross section, you always can calculate with this cross section option the utilization of the cross section, or display also stresses, yeah, on the cross section for this X place. And here you see, for example, okay, our stress is maybe almost near the limit, maybe you have to increase the cross sections. Yeah. Now could follow a step to increase cross sections, but that's clear. And if you want to go ahead with after, let's say, after you checked all cross sections and you changed it and you have a green design, then you can go to the documentation and presentation for customer. Here our program offers some more features. Maybe what is interesting and nice, if you have to, for example, to present your customers the deflection of self-weight, we give, where we are, static analysis. Now let's go to the deflection. You can display, for example, or you can give your customer for presenting your work a video file, which you can create here below tools. And here it's quite interesting to use this where we have view camera fly mode, which gives you the option to fly also into some objects. Yeah, so you can move your point of view where it's needed, and can place also and can give the customer a picture inside the model, even with results and how it's banded. No? And this is quite interesting, and I think it can show how good your work is and that it's needed, and to check all these details. The next is, if you want to print something or to give it to your client or customer, we have some organization. Yeah, you have some visibilities automatically generated, so you can display maybe all attention members or all prepared groups, but you have also the option to create your own groups. So it's possible to say, maybe this is maybe here the front frame. So let's make a slide isotrope, so, and say maybe wireframe without the rest, and now we can make here front, and let's do a second with, for example, let's show only these objects and go here to mid. No? And now you can change between two slides, and these slides we can use further for printing, but before we can print we have to create a report, and the report is now a new application. This application gives you the option to say what should be documented. In this case you can say, for example, I want to display the table of notes, and I copy this table of notes. So you have two, maybe one for base. You can say, please show me no, moment. You have a filter, and you can say, please use according numbers, and say, show me all nodes from the base. And the next table is maybe the rest. And this table shows you all nodes above, for example. So you have the option to create from one topic different tables. Then you can also say, maybe for design, please show me all tables like it is done in the background of RFEM, or you say, please show me only the governing checks and give me design formulas. And let's create a document. This means now the program exports all data from this model into another application and creates it in a table style. And this another application is not connected directly, so you can only export data or refresh it, but it's still possible to work in RFEM during you have an open report session. So we can jump back here where you get displayed all data in the style that your client can read the data like it's needed. Yeah. So all tables, all the stuff is documented with colors that he can find the data with clear description, what is what, and so on. and even our designs. Oh no, maybe here's in node table base, you get one table for base, one table for the rest of nodes. For the design, what we just discussed is, for example, you get for every member a clear design for utilization, for service, for cross section, for stability, and for serviceability. Always these three governing figures. But you still have the option to get maybe even pictures in the report. And pictures into the report, for example, we can display here a utilization picture from Steel Design, where we can display maybe all designs in a small colored diagram on member. So you can print it in report. You have here a refresh button where you can hit uncheck, then you see maybe you define I want to make a window filling sketch which is rotated up to 70 degrees and for the current plot. And now if we push this refresh option, you get a preview of the picture what should be printed into the report. And if you see, oh, this colored color scale should be outside the picture, you change it and the preview is updated, and if it fits you can print it into report. The same you can do, for example, for a model plot. So a model plot is also possible. So I deactivate it here, maybe I activate the distribution services, and now I can print into report and say maybe I deactivate this. I want to have a 0 rotation. I want to have a high of 50% of page. It should be done window filling, but it should have a 3D option, for example. Let's check if the preview is fine. And yes, and overtake it in report. And if you want to print results, it's also possible. You go again to this printer application and let's make multi-print pictures, make window filling, maybe high of picture is okay, 3D option we remove, and let's go to results, use maybe results for different load cases, maybe for 0, 1, 2, 3, for example, with the views front and mid. And here we want to present, for example, the internal forces, the normal axis forces and bending moments. So it's on you what you want to print. And if we are done, we can check the preview by updating it, and we get in the preview not only one pictures and all, the complete series of 12 pictures, I think. So he's updating now. And we get these pictures now, where they are. No, sorry, it jumped to another window, so we get these pictures here prepared in this preview, and now we can move it into the report. And it moves all these pictures into report. You see now the report is working, it overtakes all these pictures, and then we can use it. During the generation, of course, we can use the report. The only case is that we have to update the page figures, but it's already done, we can use it. So you see all these pictures now inside. And now I'm coming to one of the last features of our report. Here you see we have also a really big navigator for all chapters, what also available in Orphem. But if you have the need to create own chapters, you can select one, can create a new folder, maybe additional information, and you can place it here, or and you have an empty chapter with number of 13, and here you can bring in something. For example, a PDF. Yeah, and let's use one. I prepared maybe the material properties of the trapezoidal sheeting here by 2 pages, and I open it and bring it in to the report, and you see it's now inside. Yeah, of course we can move this into the chapter, then it's collected under the chapter 13. If you think this is not a good placement, you can place it also below maybe the materials. Then it's have a numbering of 1.2. So you have an automatic numbering what is depending on the place in Navigator, and you can decide where it should be placed. And now this brings me to the end of document and set up a protocol for the calculation. I create now a PDF of everything. This is important for me because if you use the PDF machine or engine in our application, you can use all let's say all positive points, what means I can transport not only the pure letters, then also the navigator and all information what is available on this topic. And if we open it, you get a PDF where you have the same navigator. You can jump, for example, to the table node base. Or node rest, or maybe type for nodes. So this navigator, it works for you to find all topics. Yeah. So now I jump to the picture. So he have to think a little bit about, moment, this was not my fault. It's above model in axis. So this is now one picture in the report, and if you remember, we printed it with a 3D option, and this gives your client or you the option to take a look below the model. And you can imagine you can print pictures with results or whatever into this report and give your user or client the option to watch it in detail, to turn around, or to use a section. Yeah, you can use here, for example, a section into y-axis and go through the model, and these are new options and improves the displaying of your work for your clients. And yeah, this brings me to the end of my demo. I need a little bit more time, but I hope I could show you these key features of our new program FM6, and I could inspire you a little bit. And I give back to Andreas.
Okay, thank you, Andreas, for this very nice presentation. I think you showed very well how easy it is to handle such a structure, the modeling and the design and the documentation, at least for someone who is familiar with the program. But if the attendees work with the program of the trial version and exercise a little bit, then it should be quite easy to work with FM6. Before we come to the end of the webinar, I would like to show you where you can find the recording and the model. In the next days, you will get an email with a link to that page here. Under News and Events, you can find the webinars. By the way, the next webinar will take part in 2 weeks, and that's about the reinforced concrete design. In the next, that page is not working at the moment. We need to repair that. You will get an email to that page, and there you will find the recording and the model. And I need to say thank you for your attention. Thanks to my colleagues for supporting with answering the questions. Thanks to Andreas Niemeyer for the nice presentation. Then have a nice rest of the day, and bye-bye.